मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी राजधानी।
Well, this lecture in the series of mechanics of metal forming course. Here, as the previous lectures, we covered the state of stress and state of strain concept, which was more relevant to a continuum body, but and basically it was geometry based. It was not based on material. So, whatever material, it can be applied to any geometry. So, but most often we come across in the forming processes, most of the processes where the property is also very much concerned. So, when we concern the as well as geometry, we need to know a treatment of stress strain which becomes a incremental form, so that we can predict the stresses and increments at certain level. So, in this lecture we are going to see relationship the concept of the stress strain at a point that we discussed earlier with respect to association with the property of material as well as geometry. So, if you see the earlier concepts were general, and it was all applicable to an continuum with considering material property. So, here that means we now would like to present the situation where the material behavior is at certain temperature, at isothermal temperature, and the deformation, let us take at the slow rate of, and in a very range of small strain, how can it be applied to these situations. So, the relationship describing the material behavior, we can call it as constitutive equations, which are mathematical description of the physical phenomenon based on experimental observation and is well established principles. These constitutive equations which describe the behavior of the material and not the behavior of a body, that is shape. Therefore, these equations relate the state of stress at a point to the state of strain at that particular point. These equations are generally approximations of the true behavior of the pattern, since an accurate mathematical representation of the physical phenomena would be very difficult to propose. The first, the constitutive equations for an elastic body. Let us see what happens, and then we would extend it for elastoplastic stress strain relationship in the next subsequent lecture. So, let us see first the stress strain relationship as far as the elastic, within the elastic region is concerned. We have already seen that when a uniform cylindrical solid rod of diameter d is subjected to a tensile force F or P, then we have seen that the length of the rod increases, and based on the experimental observation, the tensile test we have already carried out, and those related to stress strain curve, it was postulated that the axial stress, that is sigma, is proportional to the axial strain epsilon up to a limit which we call as the elastic limit or proportionality limit. So the constant of proportionality, that we sometimes call it as the Young's modulus, sometimes the elastic modulus. Therefore we represented by a particular very popular equation equal to stress by capital E, if it is Young's modulus E. So this law, this particular law, which is represented by epsilon is equal to sigma by capital E, it is well known, which is called as the Hooke's law, that we have already seen earlier. When the rod elongates its lateral dimensions, as the diameter we have seen, it decreases. The ratio of the lateral strain to the longitudinal strain, that we have already calculated, and that was given a name as Poisson's ratio nu. In the elastic range, we have seen that the deformation of a body depends only on its current loading and is independent of the history, any force history or strain history or rate or time, etc. We have already seen. In addition, the body always returns to its original shape when the load is removed. So that what happens within the elastic range. If we generalize this Hooke's law of uniaxial stress situation for 3-dimensional cases, where the 3-dimensional stress field or 3-dimensional state can be easily proposed, and it can be extended the Hooke's law. How one can do it? By considering that the stress and strain are proportional, if it is possible. So when one can postulate that such stress component can be expressed as a function of all the strain components. So in general, there are in fact the strain tensor that has got 9 components, or if we say the stress tensor that has got 9 components. So the 9 components of the stress in 3-dimensional state of stress, and there will be 9 components corresponding to the strain as well as. So they can be related as this particular equation, which is the tensorial representation, like sigma ij. So sigma ij is equal to C I j k l, C I j k l and epsilon k l. So please mind the notations of the tensor here, that it was explained probably in lecture number 8. So this equation we can then say that if we calculate from this, the stress, say it is sigma xx, so we can write down the component of this of equation number 2, which is sigma ij is equal to C I j k l and epsilon k l. It can be then extended corresponding to say sigma xx. So it can be written as having 1, 2, 3, 4, 5 and 4, 9 component as C x x x xx plus c xx yy epsilon yy plus c xxx zx epsilon zx plus c xx xy epsilon xy c xx yx epsilon yx plus c xx yz epsilon yz plus c xx zy epsilon xy plus c xx zx epsilon zx plus the last component as c xx xz c xz. So this equation number equation corresponding to the stress sigma xx has 9 component. Similarly, the expression for the other 8 stress components can be easily written, and whereCijkl, if you see, is the 4th order tensor consisting of total 81 components, because Ijk, I each has got I 1 2 3, so it is 9 multiplied by 9, so 81. So in the previous lecture, the stress and strain tensor, we have seen that they both are symmetric, and therefore 9 components will reduce to 6, because 3 are equal, so 3 will be equated, and therefore it would be. So this symmetry in stress and strain reduced to 81 independent constants to therefore 36 independent constants. So by considering the path, the independence of elasticity, that is the work done is independent on the starting and in positions and is independent of the path in between, it can be shown that these 36 independent constants which after removing the symmetric part are independent, purely independent, and if work done is calculated, particularly elastic work done, so if the elastic work done is the path independent, if we can say, from the stress and strain free state where the sigma ij is 0, and that is if there is no such history, and tau epsilon ij is also 0, if this is path independent work done from any historical, if there is any stress and strain existing previously to a state, to a stress and strain, say for an example a given state, say sigma ij and epsilon ij, then one can write down this equation number 4 as W, that is work done, can be taken as the summation or it can be integral over the given path dw. So dw is the incremental work done, and which dw can then be further correlated with the strain path, that is the initial strain has been 0 because assumed, and if it is strain to a final strain, say it is epsilon f, then the dw can be written as sigma I and d epsilon I. So that is the d epsilon I represents the incremental strain. So the work done can, elastic strain can be very well said that it is a deva work, that is W elastic divided by deva strain, that is deva epsilon I, and that is what is equal to the uh, sigma I. So, if the sigma I is substituted in the earlier, so and considering that deva 2 work elastic divided by deva epsilon I epsilon j is equal to, it can then be written as deva I divided by deva epsilon j and ij, capital Cij. So, if this work done, if this elastic work done is path dependent, if it is a path independent function, if it is a path independent function of the strain, then the components of this particular capital C L will be symmetric. This symmetry will reduce to 36 independent constants to further 21 independent constants. The above reduction in elastic constant is for a general material, for any material it can be, that reflects the symmetry of the stress and strain and path independence of the elastic work. So, it is known most real materials are polycrystalline, that we have already seen. That is, it is consisting of, most of the materials are consisting of single crystals and grains. That is how it is polycrystalline. And microscopic properties of polycrystalline material represents an average of the individual grain properties, that also we know. So, in polycrystalline material, the elastic constants may also exhibit symmetry, and therefore, by assuming the material in the form of single crystal, it is very easy to explain the symmetries where the elastic constant remain unchanged. The number of elastic constants, again the crystal symmetries are, it can be summarized, it has been summarized here in table 1 given here, where the independence constants for different crystal structures can that are independent elastic constant, like triclinic. If the structure is triclinic, it has around 21 number of independent elastic constants. If it is monoclinic, it is 13. If it is ortho rhombic, then it is 9. If it is tetrahedron, it is 6. If it is hexagonal structure, then it is 5. If it is cubic structure, then it is, and if it is isotropic as said, then it will have only one elastic constant. So, considering the properties to be isotropic, one can assume that the normal stress, basically sigma II, do not produce shear strain, and that shear stress, generally sigma xy, sigma yz, sigma zx, they do not produce normal strain. Therefore, the strains produced by the stress component can now therefore be evaluated using the principle of superimposition as explained earlier, and therefore this can be explained as say this strain xx, that is when one can say as the normal strain is equal to 1 by E elastic constant, and in bracket then sigma xx minus Poisson's ratio, and in bracket it is sigma yy plus sigma zz, and similarly the epsilon yy, that is the strain in y direct strain in y direction, can also be 1 by E in bracket sigma yy minus Poisson's ratio sigma zz plus sigma xx. And similarly, z component can also be written as equation number 7. Now, what will happen to the shear component of the strain? For an example, the shear stress like sigma xy, sigma yz and sigma xz. So, it must be correlated with g epsilon xy, similarly g epsilon yz and g epsilon zx respectively according to the shear other shear component of the stress. Here the g is modulus of elasticity in shear or modulus of rigidity as usual. The relationship between G and E therefore can be now established. So, one can write down equation number 8 as G is equal to capital E by 2 1 plus nu, that is the Poisson's ratio. So, in light of the equation number 8, the terms of Dievateric strain component from as evaluated in expression 7 can be very easily written as, say, that means epsilon xx, that is the direct strain, one can then be written in terms of equation 8 as 1 by 2g and Dievateric part of the stress xx, that is xs prime, that is the Dievateric part, plus 1 minus twice nu divided by capital E and the mean stress, so sigma m. And likewise one can extend this it for the yy direct yy component of the strain, and similarly the z component of the strain one can extend. Now, these substitutions is going to create a relationship between the stress and strain similar to the one which existed with pure Hooke's law. So, one can similarly see that the shear component of the strain, that is epsilon xy, epsilon yz and epsilon zx, can also be established in the same way. So, for an example, epsilon xy, that is the shear component in the plane xy, is sigma xy divided by 2g. Similarly, the yg component would be sigma yz divided by 2g, and sigma epsilon zx, that is the in the plane is shear strain in the plane zx, would be shear stress in the on the plane zx divided by 2g. So, reminding that the sigma m, which is the hydrostatic part or the mean stress, was equal to 1 by 3 and summation of sigma xx plus sigma yy plus sigma zz. So, this notation, that is equation number 9, can therefore be written in the form of tensor notation, and therefore it becomes as equation number 10, where the strain, that is the ij, can be then expressed in the terms of G, E and Poisson's ratio including mean stress. So, therefore, it can be written as two term number 1, which is tau sigma ij divided by 2g, second term 1 minus 2 nu divided by E and chronicle delta ij and sigma m. So, and sigma m, it is well known, which is equal to 1 by 3 and sigma ii. So, and again to recall that sigma ij tau ij, sorry, chronicle delta, it is 1 when I and j is same, and it is 0 when it is unequal. This with this establishing the relationship between the G and E, now let us move to the plastic stress strain relationship. As I told you, the elastic part is not very relevant under the large deformation problems. So the plastic part is more relevant with this under large plastic deformation. So assuming that the principal axis of strain increment coincides with the principal axis of the stress. So Mises, one of the scientists who worked around 1913, proposed a general relationship between strain increment and deviatoric stresses, which we would be considering later when the yield and flow chapter comes, the lecture comes. But let us take this equation number 11 here for the time being, where this particular relationship was proposed long back in 1913 by Mises. So this says the strain increment is strain increment divided by the deviatoric part of the stress is equal to a constant which is given by a proportionality constant delta d delta. So the equation number A can be written accordingly, extended equation, as d strain xx divided by deviatoric stress xx is equal to d strain yy divided by the deviatoric strain yy is equal to d strain z xz divided by deviatoric stress z xz, and it would again be equal to d strain xy divided by the deviatoric part, that is the direct stress xy, and it will be further the d strain yz, which will be equal to the sigma yz, and again when it is d strain zx divided by strain zx, it would be all equal to d delta, d lambda, sorry, d lambda. So d lambda is an instantaneous non-negative constant, which is proportionality constant, which may vary during the straining process, and therefore in terms of the stresses, this gives three equations of the type that one can take the combination from equation number 11, and therefore one can write down as d strain xx, for example, will be equal to 2/3 of d lambda under bracket sigma xx minus half under bracket sigma yy plus sigma zx close, and this closes the bigger bracket. And another three of the type can also be written in this form. So d strain xy would be equal to the stress xy d lambda. So in tensorial form it can be represented as d epsilon ij is equal to sigma prime ij d lambda. So this particular equation, Mises equation, which is for elastic strains where elastic strains are not taken into account, because as I said the elastic strains are very small, so it can be neglected, and total strain increment and plastic strain increment are therefore identical, because the elastic part is 0. This particular equation number 11, that is proposed by Vidya-Mises, was also long back in 1870 around by Levy, and the equations since then it is called as Levy-Mises equation. The details of these equations are available, we would be discussing later also. So, in light of this Levy-Mises equation, let us see the elastic plastic stress relations now. So, the stress strain relation for an elastic perfectly plastic material, as you know, it was proposed by Prandtl in 1924. So, those equations are given once again here, and it is extended version of the Levy-Mises equations, where the plastic strain increments are denoted by subscript P. So, if P is plastic, so that then one can say that d epsilon xx P divided by sigma xx prime, that is the derivative part, is equal to d epsilon yy P divided by derivative part of yy, derivative stress yy, is equal to d epsilon zz P plastic divided by derivative part in zz direction is equal to d epsilon xy divided by stress xy, that is the shear component, and therefore it is again equal to d epsilon yz divided by stress yz, and it is again equal to, that is 6 component or equality, d epsilon zx divided by stress xz, and this is equal to what was d lambda, and simply in the tensorial form it can be written as d epsilon ij P plastic is equal to derivative part of the stress, that is prime sigma ij prime d delta. These equations, that is equation number 16, it is a set of equations, therefore indicate that incremental plastic strain depends on current so that is the current value. So, it purely depends, and therefore d lambda is a constant. So, the total strain increment, if we say as d epsilon, would be the sum of the elastic strain increment, that is d epsilon E, and plastic strain increment as d epsilon P, and therefore the total strain can be written as d epsilon ij is equal to d epsilon ij E plus d epsilon ij P plastic part. So, if you substitute the elastic and plastic part from equation number 17 into equation 17, and earlier whatever we got the value of these from 10 and 16, we get this equation, that is the strain increment would be in terms of G, E and Poisson's ratio including chronicle delta, including mean stress, and d lambda, which is the Levy-Mises equation, it comes from the definition. So, this particular equation number 18 Now it is the incremental strain is function of G, capital E, Poisson's ratio, mean stress and the deviatoric part of the stress, current, and that too it is the current deviatoric part of the stress. So the equations, if you see the earlier equation 15 can also be written in the form of normal stress, giving the three quantities of the type, therefore d epsilon xx plastic part, therefore from equation number 15 it can be further 2 by 3 d lambda and the whole set in sigma xx minus half sigma yy plus sigma zz, and this three set of equations can be of the type d epsilon xy is equal to sigma xy d lambda. This equation 18 therefore has three equations of the type which is given here in equation number 21. So d epsilon xx is equal to 1 by E, this z plus 2 by 3 d lambda in bracket bigger bracket sigma xx minus 1 by 2 sigma yy close bracket, and altogether the three of this type, see d sigma xy, that is the 21 corresponds to the direct part of the strain increment and this corresponds to the shear part of the strain, and one can see here also the direct part of the strain is associated with E and the shear part is associated with G, that is the modulus of rigidity. So separating the volumetric and deviatoric strain increment from the total strain increment, the elastic plastic stress strain relation can now be established as equation number this one, which is 23. So the d epsilon ii can be written as 1 minus 2 nu divided by E and d sigma ii, and similarly the that is the deviatoric part of the strain can be ij can also be written as 1 by 2 g d, the deviatoric part of the strain ij plus deviatoric part of the strain d lambda. Since the general form of the equation which was earlier given in 15 was also given by Russell in 1930, so this particular 23 equation number 23 is also called as Prandtl-Russell equation. The equations therefore however it is difficult to use in practical cases. As a consequence only a few solutions are available which are which particularly uses these equations. In fact in most perfectly plastic material problems or plasticity problems where large plastic flow occurs, the elastic strain is therefore neglected and the plastic strain is only considered in the form of increment, and that represent the total strain increment. So this is what this particular equation 23, it gives the direct strain increment and the deviatoric strain increment, and therefore it is now established thus that these relationship where it depends on now the incremental form, and therefore it is depending because the now G and E is also included. So G and E's are the material property, therefore material property, and because the strain is there, so the Now these set of equation, that is which is tensorial form, which is in equation number 23, it correlates the material property as well as shape and size of the formation, and thus this equation would be subsequently used here. So with this you try to solve different problems, because more and more the problems are solved based on this discussion. The clarity of the different strains, particularly the increments, would become very easy, and hopefully you would be solving problems, objective type problems, on the given web. And I would like to thank you for your patience, and with the request that you will give your feedback for further improvement. Thank you very much.